to everyone. So today we are into 75% of the course. That is a day 15. And today's topic will be simulation and case study of AC to DC hybrid microgrid. So the case studies on this is going to be very interesting, and some new learning will be there along with the results of some new controller, new agile controller. So that we will be seeing. So now Sir is with us. So the session is now hand over to Sir, please.
Okay. So very good evening and happy Sunday, because I know you must have compromised your own programs to be part of this today's lecture. But nevertheless, we'll try our level best to make the class interesting. So first of all, when we talk about simulation and case study of AC/DC microgrid, so welcome you all to this mighty sponsored course on smart grid. And we're talking about simulation and case study of AC/DC hybrid microgrid. First of all, please try to understand microgrid, either it is DC or AC or AC/DC, the control logics and the operation from island to grid connection is going to change. However, one of the most important part we are going to discuss today is about the voltage control. So what happens whenever any distribution system which has been connected to a microgrid. So now what is happening, we are going a little bigger. So we have a microgrid which is either 5 to 10 buses of DC or AC or hybrid, no issue. But now this microgrid has been connected to a distribution system. Ideally, where the microgrids are connected? Transmission system or distribution system? Connected to distribution system only. Microgrids are connected to distribution system. So today, we will see if there is a microgrid which has been connected to a distribution system, how the distribution system is going to experience all the challenges due to a given fault. Due to a given fault. For an example, the distribution system, imagine I do have a 33 bus distribution system. I do have a 33 bus distribution system. And distribution systems are always radial. Distribution systems are always radial. So what will happen if it is radial means it's keep on moving from one bus to other, experiencing some sort of voltage drop in between. Okay. So if you recall your childhood, if some of you belongs to a rural village like me, where the last house of the street will experience a fluctuation, voltage fluctuation. And especially they have no fortune to have a tube light before 50 years. Only the person sitting next to the substation will experience a tube light joy, but others will have normal bulbs. The reason being, because the voltage, if it is 230 volt single phase at the substation, 11 kV substation for an example. So the last point, 11 kV to 400 volt, 3 phase, single phase close to 230, and that's keep on going. The last one will get close to, is closest to 210 to 250. But if the voltage itself is 200 at the substation, that is quite true in rural feeders, and so we'll experience around 185 to 190. The bulb will be very significantly dim, and the tube light will never glow. They will fluctuate. So what is to do? Immediately, before it gets evening, people started using electricity. Whoever switch on first, even at the last house, will experience the tube light. So we used to switch on even at 5 o'clock the tube light to make sure that it is glowing even the whole night. Okay, so that is how the story is. So what exactly happened? There is a voltage drop being experienced very commonly in case of distribution systems. Even today, it is very common. So now how do we compensate voltage drop? By putting a capacitor bank. We put a capacitor bank so that the voltage at that bus particularly can be boosted or increased to the nominal voltage. So capacitor banks are very common. When you have a long feeder going up to 5 kilometers, let's say, from one point to other, so at least there will be a drop of 5 to 10% voltage, and that is being compensated in between. After 2 kilometers, 1 capacitor, after 4 kilometer another capacitor, so that the grid is slightly balanced. If you drop the voltage, you will see like this, like this, like this. Dropping up, you will balance it out. Today, we will see that if you connect a microgrid, which is AC/DC microgrid in nature, connected to a distribution system, then what are the challenges one is going to experience? Let's say if there is a 33 bus distribution system or 100 bus distribution system or 10,000 bus distribution system, like Jaipur will be around 10,000 bus distribution system, all right? So you will not be having 10,000 microgrids, am I right? MNIT Jaipur may have a microgrid which has been connected to the 500 bus of 10,000 bus distribution system of Jaipur. So that particular bus, when I put a microgrid, that bus will certainly experience a different voltage scenario compared to other buses. All right. So let's see what's going to happen. So first of all, try to understand the meaning of voltage regulating devices. Okay. I mean OLTCs, D-STATCOMs, converters are commonly known as voltage regulating devices. So they are being used in the distribution system to control the voltage as desired close to 1 per unit, depending upon the location and its connection. Now, coordinated voltage control, popularly known as CVC, is a scheme which makes sure that the voltages are being optimally, voltage generating sources are or voltage regulating devices are optimally placed and the overall system voltage is being maintained properly. That means the objective of coordinated voltage control, so-called CVC, is to optimally utilize different compensating devices to increase reactive power reserve. So why voltage and reactive power? You know they are strongly connected. So if you have enough reactive power, what is this STATCOM? It is basically a reactive power source. So when you have those sources, means the reactive power sources only can help the voltage to be controlled. If I have a shunt capacitor, I will have voltage increase. If I have a shunt inductor, the voltage will reduce. So depending upon these reactive elements, the voltage at different buses can be managed or controlled. And to reduce post-fault voltage recovery time. Now what happens when you experience a voltage, then you will see that the voltage in most of the buses, if there is a fault in a system, what happens? You will experience low voltage. You will experience low voltage. Instead of 1 per unit, you will experience 0.8, 0.85 voltage because most of the things are disconnected, isn't it? So once you come back, okay, once you come back to normalcy, are we able to regain those voltages? Means I had a system which is 1 per unit. There is a fault. Then I experience 0.85. The fault is being cleared. Now the system is on. And now I experience 1 per unit. That you have to check it today, what is going to happen. So types of CVC, to make sure there are two different type of controllers. One is centralized voltage control and decentralized voltage control, same as your conventional controllers, and with communication and without communication. So this is one of the system which is a true microgrid to me, okay, and you can just check this diagram with an article Gururaj and myself in 2017. It is IEEE transaction, all right, industrial informatics, where we have taken 33 bus distribution system, and it is a pseudo microgrid, means we have created microgrids at a particular bus, and we have created renewable generations at some other place. So practically, if you see how the distribution system look like with different microgrids or renewable generations or loads or this STATCOM, are being connected, I think probably it will look like this. Okay, so you have the utility grid on the top, and then you see the 33/12.66 kV substation, which is in our case actually 33/11 kV substation, because it's a United States North African model. And then you have different buses, 1, 2, 3. Can you see 1 to 33 in this network? Yes. And now we like to have a microgrid. That microgrid could be MNIT Jaipur campus or IIT Roorkee campus. And that is connected at which bus? The microgrid is connected at fifth bus. Very good. So fifth bus, we have connected a microgrid. So now what I am interested to say, that if you are going to work on a practical distribution system of any geography of this country, you can capture that distribution system having n number of buses, and at a particular bus, okay, if you like to put a microgrid, or if there is a physical microgrid exists at a particular bus, please do simulate accordingly. Okay, so, and then there is a wind plant of 1.1 megawatt connected to which bus? Bus number 22. Let's see, yes, it is connected to 22. Okay, and what about, so bus number 22 is connected, bus number 5 is connected, and at bus number 1, what we have? Bus number 1, there is a red block, no? What is that red block? Huh? What? Huh? Okay, I'll tell you slowly. So there are three different type of voltage regulating devices present in this system. One is red block, one is blue block, and one is green block. Okay, so there are three things. So we have actually, that is going to be old TC. All of you, please have a look. Okay, transformer. There is a transformer. Online tap changing transformers. Do you remember? So what is the role of a tap changing transformer? Tap changing transformer? No idea? In steps. It is because there are, so at each time, how much voltage we are controlling in tap changing transformer? There are 16 steps. Ideally, there are 16 steps in a tap changing transformer. So 1 per unit divided by 16 will be close to 0.0625. Isn't it? So 1 upon 16 PU will be the voltage that can be managed in each step. So that means we have a OLTC at bus number 1. We have a DSTATCOM and DFIG at bus number 22. All right. And we have a load also at bus number 22, because loads are also responsible for voltage control. Okay. And then at V5, we have a microgrid. Yeah, everything. So voltage regulating devices, let me read it. Voltage regulating devices like OLTC, DSTATCOM, and WGC. What is WGC, GSC? Wind grid converters, okay? So basically wind converters, distribution STATCOMs, and tap changing transformers, and the DC microgrid converters are responsible for voltage control. Okay, they are responsible for voltage control, are operated in a decentralized manner without having any communication among themselves in a practical distribution network. Every bus, every device to observe the bus voltage at that particular point. So if you have a tap changing transformer connected, so it's automatic. If so, then it will measure the voltage. If it is 1, it is well good. If it is less than that, so then it will try to switch on to a point where the voltage can be boosted. Is it okay? Without having any communication means they are independently operating irrespective of the other control. So other control devices. Why the tap changing transformer is being situated in the substation itself after the utility grid. So if you, instead of getting 33 volt, 33 kV, if you are getting, let's say, 31 kV, so your output actually, instead of 11 kV, you will experience 10.5. So the voltage variation started from the substation itself. So this tap changing transformer will make sure that it is desired voltage 1 per unit, which is 11 or 12.66 or 33 or 400. And hence, the buses actually will experience the different voltages. Okay. So real-time voltage information, that's what I said, this is a very interesting case study, because it is no more a pilot. Now we are moving to a mini distribution system concept. Okay. So real-time voltage information, that is VM1, VM5, VM22, are provided to the corresponding voltage regulating devices connected at bus number 1, 5 and 22 respectively. You may ask me, sir, what is the reason for choosing 1, 5 and 22? To be honest, there is no reason. You can choose anything, it will work. All right. The idea was actually to keep microgrid one side and to keep other devices in the other side, so that actually the diagram will be balanced. Otherwise, you can connect anywhere. Okay. So let's see what is on circuit or online tap changer, OLTC, popularly known as online tap changers. Okay. So OLTC changes its tap position if the voltage of the first bus varies within plus or minus 10% of its nominal value, that is from 0.9 per unit to 1.1 per unit. So what will happen? So if it is varying between 0.9 to plus or minus 10%, so then approximately for 0.2 per unit, you will have 16 steps. Okay, for 0.2 per unit, you will have 16 steps to minus. So you can calculate each step will be what. So now, if the voltage variation at regulated bus of OLTC crosses the predefined dead band, then OLTC changes its step position. Therefore, each step variation of OLTC constitute of 0.00625 per unit changes in the voltage. All right. So if you multiply 0.00625 into, let's say, 60, how much it is giving you? What is 0.00625 into 16? Will be what? How much? 0.1? Yeah, it is giving you 0.1. So what is happening? So it will have actually positive or negative. Either 0.1 means, you see, if it is 1 to 1.1. All right. So 1.1 to 1 is possible. And if it is 0.9, 0.9 to 1 is also possible. The target, either this way or that way, it will come to 1 at any given point. So any value between 0.9 to 1.1, you can bring back to 1 per unit by this 16th step of each 0.00625 per unit. We all are power engineers. Huh? Okay, good. Now, next is actually doubly fed induction generator, DFIG, and the STATCOM. Okay. So, a 1.1 megawatt rated DFIG based wind system is connected at bus number 22. Okay, there is a wind farm of 1.1 to a substation of 0.69 kV / 12.66 kV, a step up transformer. So I like to show you here again. Please have a look. Look at the wind farm. The wind farm is of the capacity 1.1 megawatt. At what voltage it is generating power? 0.69 kV. Okay, so these are all logic questions. You need not be precise, but you must know that the wind generation of 1 to 5 megawatt are not connected to 11 kV directly. Please remember. So, have you seen a wind power plant? No, you must visit. If you see a wind power plant, you will find a substation just next to its base itself. And that is nothing but this transformer, okay, which is of 0.69/11. But in this case, the system is actually IEEE. So we made it 0.69/12.66 kV. Is it okay? So that what will happen? The bus number 22 will be injected with wind energy at a bus voltage of 12.66 kV. Now, similarly, we have a 0.8 MVA D STATCOM is also attached to bus number 22 via similar rated transformer in order to regulate the bus voltage. So the STATCOM is also connected to a substation transformer, which is having an terminal voltage of 12.66, so that the 22 bus will experience the same voltage. And finally, we have actually a pair of switchable reactive loads, each rated with 0.4 megawatt and 0.2 MVAR, are also connected at bus number 22. So we do have also load. So what do you mean by switchable loads? Switchable load means they are actually inductors and capacitors and also some resistors. So it's basically a combination of RLC. They can be varied. 0 to, you can vary basically the reactive power can vary from 0 to 0.2 MVAR. I cannot have a pure inductor, okay? So there are actually reactive elements which are between 0.4 megawatt and 0.2 MVAR. So you can vary those P and Q injected from those sources so that the bus voltage can be varied. Is it okay? So we have a distribution STATCOM, we had a wind generator, then we had a reactive load. Imagine they are capacitors simply. So to make the problem a bit simpler, they are capacitor banks which are giving you reactive power. Now we are moving to the bus number 5, DC microgrid. All right. So bus number 5, what we had at bus 5, the DC microgrid is connected through a 2 MVA rated DC-AC converter. So there is a 2 MVA DC-AC converter is connected. It includes a PV source rating 1.8 megawatt. Why we have taken 1.8 megawatt? At that time, IIT Roorkee had 1.8 megawatt of PV. All practical, no stories, all real. All right. So operated at a maximum power point MPPT with help of a unidirectional DC-DC converter and a stack of lead acid based battery of 0.4 megawatt. Why 0.4 megawatt? Because in my lab I do have 0.4 megawatt battery also, 2 banks actually. All right. So many people said, sir, your system, whether people will accept it. I said they have to accept it because real there is no story, isn't it? So I think 0.4 megawatt is connected to the DC bus with the help of bidirectional DC-DC converter. A pair of switchable DC load rated with 1.7 megawatt is also connected to the same bus. Along with this, a pair of switchable AC loads with each of the rating of 0.12 megawatt and 0.06 MVAR is also connected to bus number 5. Apart from these are basically considering the different substation loads we try to manage, but they are not exactly what it is. But we have clubbed actually 3-4 the departments and the loading of the IIT Roorkee, as I told you, even during off-peak, it is 2 megawatt at that time and maximum was actually 6 megawatt at that time. So we are creating a scenario which is almost resembles to 2 to 6 megawatt variation. Apart from the change in load rating adopted in bus number 22 and 5, the rest of the bus follows the same load rating as that of the standard IEEE 33 bus. We have not touched it. We have gone to America immediately. North America पे चले गए. वहाँ पे सारा बस US डाटा है. ये 3 बस जो है, especially the 5th bus is ours. The rest all belongs to 1 and this 22 are assumed and rest all are actually belongs to the system data. Okay, how the system can operate? There are 3 states: state 1, state 2, state 3. Any distribution system with or without microgrid has to operate with 3 different states. Today, what we do, I told you a problem yesterday that a microgrid can be used for demand response. A microgrid can be used for demand side management. A microgrid can be used for peak energy deficit management. Similarly, today a microgrid is used for voltage control mechanism. Are you clear? So it is not about having a microgrid, because when you are spending crores of rupees to a microgrid, because the system is smarter, we have to extract few ancillary support or the benefits out of the system that we have invested. Then only people will accept your idea having a microgrid in a system. All right. Microgrid is used to charge his battery when it is offload. Microgrid is used to discharge his battery when it is peak load. All this mechanism a microgrid can do. So that is what actually I'm talking about. So there are three different states: state number one, state number two, state number three. And these are the state of operations, what we normally experience in case of any distribution system. So what happens? The first one is called state number one, which is very steady state. That is when the reactive power requirement is less than 40%. Okay, so a very happy mode. So the system is fine, the reactive power requirement is very reasonable, and there is no issue. But the state number two is about the dynamic state where Q has to be 40. Now today in the system, if the reactive power is slightly less, you will have some voltage flickering or voltage issues, but the world is not going to fall. But the state two, where in the dynamic state you are expected to have proper reactive power, otherwise the system is going to collapse. And the state number three is transient state. That is where Q limit will be as high as 100%. So whenever there is a fault or sudden load changes, that case actually you need enough reactive power, which is actually as high as 90 to 100%. During steady state, there is switching of small loads, okay? Lights, fans, pumps are being switched on and switched off. You will experience different voltages, but it is not very worrisome, okay? So the reactive power supplied by the fast acting converters, which take part in the contingency situation, are less than 40% of their available rating. So if all the converters are very generous, not very much loaded, so whatever the small variation in the system, they can easily handle it. The voltage magnitude of the regulated bus are within the range of 0.9 to 1.1. So every time you see 230 volt become 220, 235, छोटा oscillation चलता है, okay? So that is my state number one. Now state number two, which is very important. In this stage, there is a sudden load switching. There is a sudden load switching. The reactive power support required from the fast acting converter, because when there is sudden load, we have to extract reactive power from the converter, which is more than 40% of the available rating. So in order to build the reactive power reserve, the reactive power support of these devices are hard limited to 40% of their rating. So all the time we make sure these converters provide at least 40%. The voltage magnitude of the regulated buses are within 0.9 to 1.1. So state number two, where we say the converters, come on, you cannot enjoy anymore, you have to give me 40% of reactive power requirement all the time. The last state, which is the state number three, is very important. When a three-phase to ground temporary fault, because fault is a very common thing in distribution system, in microgrid also. So why it is important? Because when you talk about a isolated or rural or urban microgrid, that means these microgrids are always prone to faults. Okay, so when a three-phase to ground temporary fault is triggered for a duration of 150 milliseconds. Why I'm saying 150 milliseconds? How many cycles? How many? 7.5 cycles. Okay. So it's quite high cycle. No? It's almost for a long duration. I wanted to highlight that it is for happening for a very long time. So the voltage of the regulated buses falls below 0.9 per unit. So that case, the voltage will fall below 0.9. Hence, the system enters into transient state. Here, the fast acting converters are allowed to inject reactive power up to their maximum capacity of Q equal to 100%. They all are engaged to evacuate whatever they have, actually, they will try to evacuate so that the system will be in a safer mode. Is it okay? So now, Manmohan, we will start the 16th one. This is slide number 10. Okay. So now we are talking about different comparison of CBC schemes. So probably, actually, this also probably we could start, that would be great. I think we can start from slide number 10 itself. Okay, it will help many students because it's quite complicated diagram. But one thing is very sure what we are interested to highlight, that we have different states, state number 1, state number 2, and state number 3, how the control schemes are being developed or the algorithm similar to your DC microgrid. We have developed algorithms so that the state 1 and state 2 and state 3 is being taken care. So for the state 1, actually, as you highlight, actually the state 1 voltage control devices are being operated. If you go to state 2, again, state 2, 0.40% of reactive power evacuation, and state number 3, which is my actually microgrid, will actually come to action very severely if there is a fault. I think we can start the video now.
Now, if you look into these two different flow charts, the phase to ground temporary fault is triggered for a duration of 150 milliseconds. The voltage of the regulated bus certainly falls below 0.9 per unit, and hence the system enter into a transient state. Here the fast rating converters are allowed to inject reactive power up to their maximum capacity, as maximum as 100%. Now, if you look into these two different flow charts, the CVC schemes are not very new. They're very, very old and being practiced across the world. And whereas the conventional scheme, you can see that, it is a simple algorithm. Whereas in the proposed CVC scheme, what I'm going to talk about today is slightly different, where we've taken care of the handling of different converters so that the overall performance of the system is being improved. And further, if you see what are the challenges with the existing CVC scheme. Now, the current limitations of the CVC scheme, coordinated voltage control schemes, given the importance for the speed of operation of devices only, because it really takes care or give importance to those devices who are fast, does not check for the availability of the devices for particular
Visible now? Is it visible? The CVC scheme? Okay. So now let me explain actually, instead of going for the video, let me explain. So what I wanted to highlight, just a minute. My video, I like to switch it on. Yeah, I got it. Good. Okay, I'm also visible now. So first of all of you look into the left side column. Okay, so we start. What we do, the first job is to measure the voltage at a particular bus for OLTC, DC microgrid, and D STATCOM, as well as W wind SGC, wind grid converters. Okay, so that means indirectly you are measuring the voltage at bus number 1, you are measuring the voltage at bus number 5, and you are measuring the voltage at bus number 22. That is my step number 1. So once I measure, then I have to check just come below very smoothly. If the voltage is within the limit, that is 0.9 to 1.1, if it is yes, so that means my job is done. If it is no, then I have to move to OLTC, DC microgrid, and D STATCOM. So there actually I have to make sure that the steps, because OLTC need to be operated as desired, the DC microgrid must operate as desired, and D STAT actually must operate as desired. So this is basically the moment the voltage fall between 0.9 or go above 1.1 means you are in serious trouble. Okay, so that is not acceptable. That is called my transient state. Now, if it is within which, then it could be either steady state or it could be dynamic state. So then we come to the bottom one. Is it okay? So now I'm coming to the bottom one. So when I come to the bottom one, which is either steady or dynamic, so come down. Now, if the voltage is at 1 per unit, if the voltage is at 1 per unit, that means it is fantastic. There is nothing. If it is yes, then I think everything will be at their operating points. All will be at their reference point. The job is done. There is no issue. But if the voltage is not 1 per unit, then actually Q required will be less than 40% under my steady state operation, state number 1, is it? And then we see whether it is going to be a steady state condition or it's going to be a dynamic state conditions, and accordingly we move forward. Now the second one, the OLTC steps, either it can be increased or decreasing as per my desired, because everything is between 0.9 to 1.1 scenario. Now let us slowly move to the right hand side. The right hand side, what is happening is a new concept, because this is what you see in the left hand side. It's a practiced concept as on today. So there is no innovation. But what the admired lab of IIT Roorkee brought innovation to this voltage control scheme is the right hand side. Okay. So right hand side, actually you could see the blue block, no? That block actually being now changed in a different way. So what we are saying that, look, if the voltage is within 0.9 to 1.1, fantastic, no problem. If it is not, then you go to transient state. If it is yes, then you go to steady state. As per the OLTC, we are not arguing for any changes. But below that, actually, if the DC microgrid is experiencing, okay, there is a fault, okay, and the delay period actually passed. Are you clear? So if the delay period is not passed, then we go to, because there is a fault. I'm talking about there is a fault. There is a fault, and that fault is actually happening for reasonably long time. And there is a delay also occurring in the coming back to the normal system, isn't it? So if there is a fault, immediately it comes back, there is no issue. But if it is not happening, so please have a look. So DC microgrid, I'm concentrating on, first let us see OLTC. Now the voltage is between 0.9 to 1.1. Now I'm coming to OLTC. I'm saying you increase or decrease the tap accordingly. If it is going to be 0.95, what I will do? I will move to 1. If it is 1.6, I will come to 1. Am I right? So that is the job actually I can do through OLTC, wherever it is there. Now, second case is my DC microgrid. So DC microgrid, if the voltage is within VM 0.9 to 1.1, but actually there is no transient state, there is no serious fault, everything is smooth, that I like to know whether there is any delay period actually passed. Delay period passed means any steady state to dynamic state. The movement of the state, whether this has been passed for a little bit longer or not. Now, if it is passed, yes, then we say actually the voltage at that bus will be set to 1.0 per unit. And if it is no, then actually I go for the steady state, as actually all the reactive power will be set to a 0 because no extraction from the converter. Again, when I come to VM, the per unit voltage, if it is 1.0, then I see whether it is 1.0. Yes, again I give my reactive power status as 0. If it is no, then I come to calculate what is my reactive power requirement. So how do I calculate reactive power requirement? Under root S square minus P square. Okay, so that I calculate. If once I calculate, and then if it is supply the reactive power accordingly, if it is not matching, and if it is matching, then your Q set will be under root S square minus P square. So basically, this is a control strategy which decides how your reactive power operating points of different converters being set at a operating point depending upon the required reactive power, and the same story is for the dynamic state also. I think now we can go back to the video because they were not comfortable with the picture here. Okay.
Operating conditions. All the fast acting devices are considered for injecting reactive power simultaneously along with slow devices. So what we do when it is from stage 1 or stage 2 or stage 3, all the reactive power injected devices are instructed to inject as maximum they can, and in that process the fast acting devices are always regularly participating in injecting reactive power, and the slow devices unfortunately may not be able to contribute by the time all the fast acting devices do contribute whatever measure contribution they can make. But that's not a good idea. In the proposed model, what we have suggested, utilize the devices more effectively. Even the OLTC, STATCOM, DFIZ, DC microgrid, all of them have to participate simultaneously, by which it improves the voltage profile of the system at large. It improves the fault write-through capability of the devices. It also improves the transient conditions of the systems. Now, how it is being proposed here? The first stage, identifying the operating conditions of the grid. Based on the real-time voltage information from the voltage regulating buses and the reactive power injected by the fast acting converters, a particular operating condition of the grid is identified. And then in the second stage, checking for the availability of the devices and assigning the master and slave role. So who will act as a master and who will act as a slave depending upon the fast acting or slow acting devices. It is required to first check for the availability of the device for a particular operating condition before assigning any role to it. For example, OLTC and DC microgrid are used during steady state and dynamic state, whereas the wind generators and these STATCOMs are available throughout all the 3 states. Now, the final state, introducing the time delay in operation. For example, you want some slow device to be acted before the fast devices, then a delay in action on those fast devices can be incorporated so that the slow devices can inject the reactive power, and further the fast acting devices can come to action. So as an intentional time delay is inserted for all fast acting devices like WGSC and DC microgrid, DCMG converter along with the DSTATCOM. This ensure that the slow acting of OLTC would complete its action. So as we discussed earlier, when all those fast acting devices come to action, then the slow acting devices may not be able to contribute much. So please allow the slow devices like OLTC to act first, and then the fast devices can come and follow them. After which the fast acting devices are allowed to operate. The minimum delay time is calculated for each and every bus where the fast acting converters are connected. If the waiting period is less than this delay time, then the OLTC might not complete its action. And this is what the proposed CPC scheme, because most of the control schemes we have discussed in past, so I'm not taking a lot of time here. But as a whole, you can see that this is basically DCSC bidirectional converter implemented with the proposed CPC scheme. And whereas we talk about actually the modeling for DC grid bus voltage, and this talk about the degenerate duty ratio for the bidirectional DC-DC converter of the battery, and the final one talking about the track
Friends, let me get into the PPTs because the pictures are not very clear in the video probably. This may be the problem with YouTube probably. I'm not very sure, or it is maybe some kind of alignment in the video recording time. It's almost very old things. No worry. So, and this might have been no. Sometimes Manmohan. Sometimes actually, if they are being squeezed to a PDF and posted something like some kind of compromise might have been done. Whereas in the PPT, you see it is in the right form, so they are the compressed pictures. So no worry. So is it okay? Why my slide is not changing? Slide is not changing. Oh, it's okay. Great. Okay, great. So, first of all, let us try to understand what are the limitation of the existing voltage control schemes. Okay. So, given importance for the speed, am I audible to all the? Am I audible, dear students? Please say yes. Yes, thank you. So we'll get into the presentation slide only. So what are the limitations of existing CVC schemes? So given importance for the speed of operation of the device only, does not check for the availability of the device for particular operating conditions. All the fast acting devices are considered for injecting reactive power simultaneously along with the slow devices. So what are the problem with CVC? Because you have multiple devices. Okay, so everyone try to operate. Everyone try to operate, and they are actually decentralized control mechanisms. When everyone is interested to operate, that means that some of the devices which are expected to come quickly, they may come little late, and some bus actually which is not required, they may actually act fast. So there is a issue related to your controlling devices. So what are the advantage of a proposed CBC scheme? Utilize all the devices more effectively. What is saying? Someone is saying so not available. Not audible. Am I not audible? Audible. I think, can you check your system, please? Switch it off and join again, probably quickly. What is saying? Audible now?
Camera on.
Oh, yes, okay. I think everything is okay. Audible camera. All right. So, camera is also on? No? Yes, not. Okay, okay. They like to. All right. Am I audible and visible? Okay? Yes, it's clear, sir. Thank you. Prem, it's fine now. So the advantage of the proposed CBC scheme, where we say how we can utilize all the devices more effectively, improves the voltage profile of the system at large, improve the fault right through capability of the devices, improve the transient condition of the system. So in the proposed CBC scheme, we have gone more rigorous, especially giving the fault right through capability. Means if there is a fault, still the system can survive until unless you come back. What do you mean by fault right through capability? There is a fault. So you experience voltage challenges. Am I right? So the system must have enough reactive reserve to manage the show till the time the fault is being cleared. So what will happen? There is a fault. Still we don't realize the voltage fluctuations. Okay, so that is what actually the new CBC scheme proposed, how that fault right through can be taken care. Yeah. So first of all, the proposed CBC scheme, try to understand, the first stage is to identifying the operating conditions of the grid. Identifying the operating condition of the grid based on the real-time voltage information, from the voltage regulating buses and reactive power injected by the fast acting converter, a particular operating condition of the grid is identified. So what you do? First of all, at bus number 1, bus number 5, bus number 22, you measure the voltage and decide actually what action need to be taken. The second stage is actually the master slave concept. That means which is required to first check the availability of the device for a particular operating condition. Can anybody is there to evacuate the reactive power, whether they do have something or they've already evacuated. Am I right? Operating condition before assigning any role to it. I am forcing my converter, the microgrid, to extract reactive power, but it has not. That is a very important part actually you need to identify. Who are the devices in the system are currently having some reactive power reserve with them and which can be evacuated. So OLTC, DC microgrid, steady state for dynamic states, and for wind and DSTATCOM be available during all states. So for wind, grid converters, you need not worry. For DSTATCOM, you need not worry because they're made for that. However, the OLTC and DC microgrid, those two devices actually you need to understand. For example, OLTC. Already you are at, let's say, 0.85. Even if I switch on the 16 steps, still I cannot attain 1.0. If it is, let's say, 0.75, what you will do, Bichara, actually? You cannot do anything. Even at 0.75, maximum it can come to 0.85. So that is what the second stage we need to identify who has to be communicated to act on. So the third stage is introducing a time delay in your operation. Introducing a time delay, because depending upon the situation, you have to evacuate those reactive powers or you instruct the controlling devices to act, but you must also know that who is currently ready to give that. Am I right? Otherwise, what will happen? You have instructed a fellow whose own delay time to act is, let's say, 0.5 milliseconds, but you want something to happen below 0.5 milliseconds, and then you are not going to be successful. So an intentional time delay is inserted for all the fast acting devices like WGSC, DC micro. Actually, what is happening, if you do not allow some delay to the devices, the moment they experience some voltage, because they are not able to know what to do. Other reason also they will act. That we do not want to happen. So an intentional time delay is inserted for all the fast acting devices like WGSC, DC microgrid converters, DSTATCOM. So this ensures that the slow acting OLTC would complete its action, after which the fast acting device are allowed to operate. Okay. Are you getting my point? So always actually we allow the slow acting devices to come the fast. The minimum delay time is calculated. Otherwise, what will happen? The slow acting devices will never act. They will never act because these fast acting converters will jump into the problem. So the minimum delay time is calculated for each and every bus where the fast acting converters are connected, specific to bus number 5. If the waiting period is less than the delay time, the OLTC might not complete its action, and this time delay has been calculated accordingly based on the time required for operation to OLTC to change one step, because it's a physical system, one step to other, it will take some milliseconds. And VOLTC is per unit change in voltage due to single step change of OLTC. All right. Now, these are the, as you see the control diagrams where we were talking about. So you could see these are all, as I told you, RSGate in RTDS. Okay. So those who do not have actually RSGate software, as I told you last time, you can start with actually PSGate. You could see how these control blocks are being designed, and this you can do at your own level. Actually, you can model this without much of difficulties, and you could see, for example, 0.00625 extreme corner time we are given actually 350 milliseconds, and you are given a voltage error and blocking. So this will act actually depending upon the commands actually that you set. Now, moving to the next system parameter side. So all of you have a look, the electric grid. We'll continue. Electric grid, which is a rated voltage of actually 33 kV and the rated frequency of 50 Hertz. And OLTC substation transformer, the rated power is 10 MVA, primary voltage 33 kV, secondary voltage 12.66 kV, leakage reactance of 0.15, DSTATCOM, it is both the capacitors 2000 microfarads, DFIG, this is 600 volt DC link voltage, and then PV parameters, shunt resistance 100 ohms, series 0.5, short circuit current, open circuit voltage, they are all specific. Solar irradiation assumed to be 1000 watt per meter square, number of panels in series and parallel 24 and 300, power rating of each panel, battery rating is also given to you. So every device connected at bus number 1, 5 and 22 are being identified. So in order to validate the effectiveness of the proposed scheme, the system is tested under all three operating states of the grid. What is the state number 1? Steady state. What is state number 2? Dynamic. State number 3? Very good. So the modified IEEE 33 bus distribution system is simulated in the real-time digital simulator, that is RTDS or RSK platform. Now these are the steady state operation of DC microgrid. As you could see, they are for actually PV outputs, battery power, and real power supplied by the DC microgrid. So all the three, PV, battery, and microgrid power output, you can see how they are being managed. And the proposed CVCs, you know, whatever the condition they start, they become steady state actually after few cycles only. Now, in case of actually dynamic state of operations of various devices at different AC bus in the distribution system, also you can have a look for STATCOM and also for your, you know, all of you, let me zoom little bit for your benefit. Okay, so have a look. Now, real and reactive power, loads and buses at 5 and 22 is known to you. The first one is going to be your state number 1, steady state, and second is going to be the state number 2. And you can see there are three actions proposed, existing, and without CBC. The black one actually without any voltage control. Okay, and the red one is actually existing practices, and the blue one is going to be the proposed CVC scheme where the OLTC tap changing positions are being determined differently. Now, similarly for the DC microgrid, you can say there are three different scenarios. And finally, for the STATCOM, you can see, and the real power and reactive power supplied by the wind generation characteristic is also given to you. So each every device during state number 1, state number 2, state number 3 can be easily calculated. But in the meantime, if you refer to the 2017 IEEE transaction on industrial informatics, where all the diagrams are available, so these are actually selected patches, but you will be able to, you know, refer it whenever you are referring those simulation results. Just I wanted to highlight, but such kind of simulation results within your RTDS you can generate. Am I right? This is another very interesting profile, which is just have a look. So you can say that there are three states: state number 1, state number 3, which is the transient state, and state 1 and 2 voltage profile of regulated bus are given to you, 6A. 6B, state number 3 voltage profile of regulated bus, and state 3 operation of various voltage regulation devices. Okay. So if I zoom it little bit, all of you please have a look. I think so. Let me come this way. First, focus here. Okay, this diagram. So what you see, the voltage bus number 22. Bus number 22, voltage in per unit. The state number 1. So there are three lines, but you focus on the proposed CVC for an example. Okay. So there are three lines based on 3. So we are comparing how the proposed one is slightly better than other models. But without CVC, you could see there is a risk involved. However, in the existing CVC, the red one, and the proposed CVC is the blue one actually. So it's a 22 bus voltage is being managed. So could you see it is almost at 1 per unit. It is almost at 1 per unit. And but actually the last state number 2, this model is actually slightly improved version. Okay. And similarly, if you move to bus number 1 voltage, it is almost very nice. There is no issue at all. But bus number 5 had a very interesting. So the voltage profile, bus number 5 is important to you. The voltage profile of the proposed model is much better compared to any other model. So that is one, the blue one, you could see the voltage profile is fantastic. And then moving to the second case, the right one side, bus number 22 again, of state 1 to state 3. So there is a transient, probably you could see there is some switched on and switched off immediately, some switching activity happened. So you could see how this works. And but the last smaller diagram, if I zoom it, you could see the right hand side. The blue one is almost perfect, perfectly smooth actually. Am I right? So this is what has been claimed. The same thing for even here also, you see everywhere the voltage profile become better compared to, and the delta V, you see the change in the right hand side, it shows that the proposed algorithm experiences a better voltage profile at bus number 1, 22 and 5. All right, and they are actually, because this portion which has been zoomed, okay, is a transient study, you see left hand side, there is a small circle. All right. Actually, that circle is being actually zoomed to say that actually which is better, because they almost all look similar. Okay, you could see there is a huge voltage variation between the existing practices and the new practices. Now we can slowly move to this one. So reactive power supplied. So first of all, see what is the OLTC gentleman is doing. The OLTC, if you see, no operation, because in dynamic case, because there is a transient, OLTC is nothing to do much there, okay, because of fast. But you see microgrid has come to action. So this is important to make now, all of you. So reactive power supplied by the microgrid, by the DC microgrid, is not enough, because, however, the wind is providing reactive power supplied by the wind, the blue one. Could you see? There is a small supply, and by the STATCOM is more active here. The STATCOM is also helping to get into the reactive power supply. So what we are learning that in any system, any microgrid, the conclusion is that the STATCOM and wind generators, they two devices will come to help you for reactive power support during state number 3 significantly, not the other devices. So that is what actually we are concluding at this stage. Right. So sometimes it will show, because the black one for the steady state, actually the black one also can do better, because it's a decentralized mechanism and you're able to do better actually at a particular bus. But only in the transient actually the classical techniques, actually the conventional, without, it's not going to help you much. So this problem actually is only for fault right through. When there is a transient, when there is a fault, then only we like to show that the existing system is going to fail. Okay. Now I will tell you what is the interesting part here. Let's say if you have an existing system, there is no control mechanism, nothing. Okay, and the body is disconnected, the feeder is disconnected. What will happen actually? My voltage profile will nicely improve, because the loads dropped. So when the load reduced, the voltage profile will be better, no? That's what this black line is showing, isn't it? It is always better, but that betterment actually, if it is too high, let's say 90% load curtail, so that case you need to observe the reactive power. That control mechanism, it will go out of control actually. All your devices will burn. So that control is not there with the system, without CBC. So I think we just a minute. Yeah, good. So the RTDS simulation result, this is your 33 bus profile. First one is going to be a steady state, and second is going to be the dynamic stage. So all of you please have a look. If I zoom little bit, you will come to know. Okay. The blue one is certainly going better. What is the blue one actually? Blue one is the voltage profile of different buses above the red one. Okay, so the existing CBC scheme, not much actually, for example, but instead of 0.92, if you are experiencing even 0.925, that itself is considered to be a better achievement using the improvement in the voltage profile. And you tell me why the voltage profile is showing like this actually, because the voltage profile is coming down and again it is increasing, again coming down. Why it is happening? Actually, they are plotted based with reference to the bus number. And if I go back to the master, all of you please have a look, because this is basically one sort of yeah. Yeah, just all of you please have a look. Could you see this is the 33 bus system, na, right hand side, and the bus, how the buses are numbered. It is actually 1 to 18, and then I moved to actually 19, 20, 21, 22, and then I moved to actually 23, 24. So the bus voltage of actually bus number 1, 2 and 19 and 3 and 23, they're almost actually same. Are you clear? So the feeder voltage actually will drop slowly. It is keep on dropping. And then I'm like 1, 2, 3, 4, 5, 6 up to 18, it is dropping. Again, I'm moving to 19. Again, it will drop. Again, 23. Again, it will drop from actually 23 to 33. So because of the numbering, because the XS6 is the bus number. So only for 1 to 18, it is a feeder, it is fantastic. But again, I'm jumping to 23, 24, 25, up to 33. And hence it is going up very close to 1 per unit. Again, it starts reducing because of a feeder. Is it okay? So do not really get confused with this voltage profile, because most of the time you say, what is happening? Why it is oscillating? So suddenly, so 1 to 18, and the top three, they're actually that 19, 20, 21, 22, and then actually 22 to 33. Okay, good. So these are the voltage profiles. And then steady state conditions, state number 1. This operation of DC microgrid is quite important. So as per the proposed CVC scheme, during the state of OLTC and DC microgrid converter act as a master. OLTC and DC microgrid act as a master, whereas DSTATCOM and WGSC act as a slab. Slab in the sense because they are the fast. So, we made actually kind of, the slow devices as masters. Okay, so now the result of DC microgrid with proposed PVC scheme are shown in figure, already explained very nicely. So the interval T, the DC microgrid starts feeding real power to the utility. In the scenario, the DC bus voltage regulation is achieved by supplying excess power from the DC microgrid. So all the graphs that you have seen, those graphs are being explained in a theoretical mode from one to other. All right. So during the interval T2, the PV output is decreased due to fall of PV radiation, and hence the real power supplied to the utility reduced to 0. And during time interval T3, there is a switching additional DC load within the DC microgrid, and the deficient power is supplied by the utility grid. Thus, in spite of all the switching dynamics, the controllers of various converters of DC microgrid perform satisfactorily. The DC grid voltage is regulated at 1200, that is 12 kV, during all modes of operation. Now, state 1 and 2, that is steady state and dynamic state conditions. Operation of various voltage regulated devices. The objective of the proposed CBC scheme during steady state condition is to increase the reactive power reserve of the DSTATCOM and wind grid converter, and also to improve the voltage profile of the overall distribution network. In case of without voltage control scheme, all the voltage regulating devices rush towards regulating the voltage of the respective bus simultaneously. So what will happen? The bus number 1 will try to meet out their voltage, bus number 5 will try their own voltage, and bus number 22 will try to. So everyone will try to help their own buses, whatever best way they can do, without any concern of the reactive power reserve. They don't mind actually what I have to evacuate, or what I need not do. So that's why the control mechanism, to make this all fellows, keep your capability with yourself, only when I instruct, operate. That is what the control scheme is all about. So making That means giving an instruction to the controllable devices, especially converters of the system, to act only when there is master is giving you instructions. Otherwise, the OLTC is poorly utilized with only one switching all the time. So it is there sitting all the time, not having any responsibility, engaging everyone in a class. Okay. Now, in case of existing CVC scheme, though there is an additional switching of OLTC, the DC microgrid converter is poorly utilized because all the fast acting converters along with OLTC are operated simultaneously. Once DC microgrid, D-STATCOM, VGSC reaches 40% of their rating, they are stopped from injecting reactive power anymore because they all want to act smart, So they say, come on, let me participate. Until unless there is an instruction, what do you say? The moment you reach 40%, just cool down. Because again, in future, you need some more reactive power to be given to system. So however, the proposed CBC scheme fully utilizes the OLTC and DC microgrid converter by providing the intentional time delay in operating of the DC microgrid converter. Thus, the voltage profile of the regulated bus 5 is improved by an amount delta V. The voltage profile of the entire distribution system is improved in case of the proposed scheme that you have seen already. The reactive power reserve of D-STATCOM and WGSC in the case of the proposed CBC scheme shows a significant increase by a maximum amount of reactive power injection, 40%. From the wind, it is 40%, and by a minimum amount from the D-STATCOM is 14%, and from the wind, it is 15%, compared to existing CBC scheme, respectively. Furthermore, the reactive power reserve of the proposed CBC scheme is increased by a maximum amount of D-STATCOM by 59% and for the WGSC by 56% and by a minimum amount of 19% and 15% opposed to without CBC scheme respectively by imparting time delay in their operation. In order, coming to the dynamic state finally, in order to study the performance of the proposed CBC scheme under dynamic state condition, load at bus number 5 and 22 are increased by 100% at instant T4. Okay. So when there is a switching basically, okay, there is a load increase too much. So as a consequence, the voltage at these buses will fall down from 1 per unit to 0.8 or 0.85 very seriously, okay, which the D-STATCOM and WGSC increase their reactive power injection after passing through a delay period. So what will happen? There is a switching, load increase, voltage drop, and these two gentlemen actually come to action, both your D-STATCOM and wind grid converter. Immediately after reaching 40% of their capacity, they are forcefully stopped from injecting reactive power anymore, in order to retain the same reactive power reserve as that of the existing CBC scheme. So even though they are fast, we say come up to 40% and then cool down. So what may happen, you drop from 1 to 0.85, then you discharge something, so probably you'll be at 0.91. Okay, the story never ends there. However, the reactive power reserve of D-STATCOM and WGSC in case of the proposed CBC scheme is higher than that of a without CBC by an amount of D-STATCOM 31% and wind actually 52% respect. In spite of additional switching of OLTC in the existing scheme, the voltage profile of the overall distribution system with proposed scheme is better observed in 7.8. So what the scenario says that, instead of randomly operating your reactive power control devices, you operate with an instruction. Okay. So what you see that in the whole proposed algorithm, they say the D-STATCOM and wind, grid converters are being operated, but not being completely evacuated. And because of which the system voltage profile is reasonable, simpler. What happens if I evacuate, let's say the D-STATCOM evaluate everything. So it is 1 become 0.89 and then become 1.1. It may, if you inject overreactive power, that is also not good for the system, no? So you have to be slightly careful. So moving to the transient state condition, a 3-phase to ground fault is introduced. This is very important. I need all of your attention. Also note it down. A three-phase to ground fault is introduced into the system for a duration of 150 milliseconds. Means the fault is serious, okay? Due to which voltage magnitude of overall system falls below 0.9 per unit, assuming it is 0.8 per unit, okay? So during this state, what will happen? Your wind grid converters and DSTATCOM place the master role and inject reactive power up to their maximum capacity. The OLTC and DC microgrid are made slaves and hence does not take part in the reactive power injection. So what is happening? You have to decide who is master, who is slave, under what condition. In the transient state, I think the fast acting actually wind grid converter and these STATCOMs are made masters. The other slow devices are made actually slaves. The DC microgrid is isolated from the utility grid and operate in an islanded mode of feed the local DC grid. Okay, when there is a fault, at least the microgrid we operate in islanded and we evacuate the reactive power from the master, that is wind grid converter as well as DSTATCOM, and OLTC and DC microgrids are not. DC microgrid anyway isolated and OLTC is keeping quiet. Okay, mama. The gauge for deciding the efficiency of the control scheme is the ability by which the system recovers from transient state at the earliest. Your control system is, your algorithm is beautiful if you're able to recover from the fault. So what has happened now? There is a fault, DC microgrid isolated, reactive power is coming from the wind grid converter as well as DSTATCOM, and OLTC is sitting ideal, okay? So it can be observed from figure 6b, if you refer, that as soon as the fault is cleared, the regulated bus start to regain the voltage. Slowly, the fault is cleared actually. That means, what does it mean? Fault is cleared means for 150 millisecond, the system could sustain the voltage collapse. The system could contain that voltage collapse because of this grid converters evacuating the reactive power. And by the time you clear the fault after 150 millisecond, and that time system become normal and you can bring back your microgrid, DC microgrid to action. So as soon as the fault is cleared, the regulated bus starts to regain its voltage. However, due to the increase in reactive power reserve, in case of proposed scheme, the system quickly reaches to 0.9 per unit by a duration of delta T1 compared to the existing CBC scheme. This is just for highlighting your article actually. But the theme of the concept, as I told you, you have a system, there is a challenge, there is a voltage deviation, you operate your reactive power voltage control devices, that is for steady state. For dynamic state, it's okay, but in transient, you isolate your microgrid, take maximum reactive power close to 40% from your fast acting devices like grid converters of your wind as well as DSTATCOM, and then slowly, once the fault is being cleared, then you bring back your microgrid to the system. Thus, the proposed CBC scheme need less fault voltage recovery time in contrast to the existing scheme. Further, it can be observed from figure 6b1 that after entering into the steady state, the system reaches 1 per unit much faster in comparison to other scheme due to the better utilization of DC microgrid converter and OLTC. I think this is a good idea. If you're writing an article, you can summarize the best practices of, at the end. This is basically result conclusion section. In addition to this, the proposed scheme has better voltage regulation compared to existing schemes after entering into steady state from transient state. The operation of various voltage regulating devices is displayed in figure 6c, from which it is evident that once the fault is clear, the system rebuilds the reactive power reserve. Coming to a conclusion, the proposed CBC scheme increases the reactive power reserve of DSTATCOM, wind grid converters, and also improve the voltage profile of the overall distribution system during normal condition. Because of master and slave control mechanism, we are not evacuating all the reactive power. We are very carefully, precisely utilizing the reactive power resources available in the system. Furthermore, the proposed scheme is also targeted to reduce the post-fault voltage recovery period in the system. An intentional time delay is introduced for all the fast acting converters for achieving the set objective. So indirectly, we are not allowing the fast acting converters to act fast. We want them only to act actually when there is a fault, serious fault or dynamic fault. Otherwise, imagine even in a steady state, they evacuate everything, and next actually there is a fault, and they have nothing to discharge. So that is the problem. So thus OLTC and DC microgrid converters are effectively utilized to improve the overall voltage profile of the distribution system during steady state and dynamic state conditions. It was observed that the proposed CBC scheme shows improved performance in comparison to CBC scheme. That is fine. So I think the first article is very, very important. All of you please refer. Whatever I talked here, a novel decentralized coordinated voltage control scheme for distribution system with DC microgrid, Dr. Gurraj and myself in, it is almost 2017 article. So all of you can refer. And with this, I come to an end. Once again, the interesting part that each and every lecture become an output of a IEEE transaction. Am I right? So every day you are solving at least one chapter of a PhD, a minor problem we are solving. Okay, you're reading a IEEE transaction, you are understanding it, and then you're moving to the next. So at least we will cover 20 IEEE transactions during the course. Okay. Almost 15 transactions are being covered as of now. Okay, with this note, we come to an end. Thank you very much. And if you have any questions, please feel free to ask. I think Chandrasekhar, thank you a lot. Okay. Thanks, Chandrasekhar. You see, every device can act. What is happening? Let's say you have actually 3 devices.
You are answering that question.
No, he's not, they're not able to listen to me. I'm answering the question only. Yeah. So there are actually 3 devices. Let's say one will be acting after 1 millisecond. The other is acting after 2 milliseconds. The third is acting after 3 milliseconds. Now, what is happening if you do not have any control over their actions? Then all the time, the device which is fast acting of 1 millisecond will come to action and try to evacuate all its reactive power. Am I right? The intention of this proposed scheme is not to evacuate the reactive power of a particular device in one go. We like to optimally utilize the reactive power reserve available with all the devices in the system. Isn't it? So that is the only reason, because if there is a transient load variation or there is a fault, okay, so there is a time is an issue. So the quicker devices has to come. If something can be managed with a OLTC, why do I call a faster device? That is the only intention. Because only when there is a dynamic scenario, then the fast acting devices act more effectively compared to the slow devices. Is it okay? I think someone is saying something. Reply. He understood? She understood? Okay, good. Thank you. So that is the basic philosophy of this management. Any other questions, if any? Chandrasekhar?
Okay.
Yes, he said. Any question is there?
First perfect question.
Please.
Chandrasekhar ji, please unmute yourself and ask directly. Actually, we could not understand what you are asking about power factor. You can unmute
Sir,
yourself.
this
ask
regarding the power factor management in microgrid, sir.
Yes, please speak.
It's power factor management in the microgrid. How it varies and how it can be
I could see
compensated.
his typed S.
चंद्रशेखर जी बोलिए.
हाँ सर, ये पावर फैक्टर के बारे में माइक्रोग्रिड में कैसा वो बैलेंस हो जाएगा?
Voice is not audible.
सर
बोलिए.
I'm talking about the power factor management in the microgrid.
Mm-hmm. Power factor. Okay, got it. The question is actually power factor management in microgrid. So ideally, we don't manage power factor in a microgrid, but we manage actually reactive power. So indirectly, the power factor is managed. So we don't call it as a power factor management, but we call it as a reactive power management scenario. Is it clear, Chandrasekhar ji?
And almost all the motors, all I think we are all having a RL load. So more of the lagging power factor will be there rather than the leading one in that case. So that's how that question has raised, sir. That's all.
No, you're very right. Actually, what exactly the challenge is highlighting is that in a microgrid, if I have lot of PVs, let's say, and I do connect that PV to motor loads, then who will provide that reactive power? That is the biggest challenge because I don't have. But we are talking about a system, the reactive power. Sorry, the reactive power is already existing within the system that you are pre-assuming. So if you have lot of motors, and if you like to run a microgrid, then you must have a DSTATCOM in place. Otherwise, the reactive power may not be available to you. So, Chandrasekhar, it is not possible to have a PV system and having 100 of motors and pumps running actually. So, for that, actually, we need to have additional reactive power support, and or you can have DC motors everywhere. Instead of AC motors, you can go for DC motors actually to manage your reactive power requirement. I think otherwise the converters have to act to compensate your reactive power requirements. So the PV inverter converters, I think they have to evacuate the required reactive power for the system. That's the only way. There is no other way out. Thank you.
Okay, sir. Thank you, sir. Thank you, sir.
We come to end today, and thank you very much for joining the class on Sunday. And that, yeah, sorry.
Thank you very much for joining the class on Sunday. Now it is 6:30, if I'm correct. Yeah, 6:40. I think it's a time to go for a holiday time. Okay, go ahead. Bye-bye.
Thank you, sir. Thank you also. Thank you. Okay.